Hello and welcome to today's webinar about the evolution of in-vehicle networks towards a zonal architecture. My name is Ralf Österreicher, and with me today in the studio is my colleague Jitu, product manager for oscilloscopes.
Hello.
So let's have a look what you will see and learn today. So first we will have a look into the challenge and the evolution of the in-vehicle network architecture. Then we will have a brief look into the transition from a domain to a zonal architecture. Then I will hand over to Jitu, who will explain in detail the automotive Ethernet, the need for testing, and will also give a practical demonstration. And then we will also have a brief summary of the technology and the testing. We all experienced over the past few years a drastic change in the automotive industry. There are a few trends coming up now that all of them have a strong implication for the future of automotive electronics and software. The industry is continuously striving to realize higher levels of autonomous driving. So nowadays, level 1, level 2 is almost normal. First cars are on the road now with level 3, and soon we will also see level 4 and level 5. But that's not it. There's actually even more. So the car of the future is autonomous, connected, electrified, and shared, which is also the acronym for ACES that you might have heard already a couple of times. What is the challenge of those new trends, of the ACES trends? Well, the developing trend from a traditional vehicle design towards the ACES requires the secure handling of data from an increased number of complex sensors. So the number of sensors is drastically increasing, and all this also has to be managed. Moving towards the ACES trends, such as fully autonomous driving or connected cars, requires therefore a fast in-vehicle network supporting high computing power and high data throughput. Also a reduction of the in-vehicle network complexity, and also efficient power consumption and weight. What is the evolution of in-vehicle network architecture? So the architecture, as we know it from the past, is not sufficient anymore to handle all those new trends. So the in-vehicle network architecture evolved already from a distributed gateway architecture with independent ECUs towards a domain centralized architecture. In that domain centralized architecture, vehicle systems are grouped by functions, and where a few domain controller units covering one vehicle domain each, such as connectivity, chassis, or infotainment. However, the communication is limited between those domains that are controlled by a central gateway. With the domain centralized architecture, you can drive up to level 3 autonomous. For future cars, you need a zonal architecture where the vehicle domains are grouped into several zones, and in each zone, devices are connected to a locally installed zonal gateway, which also brings the benefit of short cable lengths, so it's not so rigid and not so expensive. So all the sensors, they are actually closely connected to the gateway. Each zonal gateway is connected to the central computer via high-speed Ethernet. This is what Jitu will explain then more in detail, and the domain functionality is handled in the central computer. Having this redundancy with the zonal architecture, you can already drive above level 3. This overview given by Marvell at the latest Automotive Ethernet Congress in Munich in 2022 shows very, very well the difference between the domain architecture and the zonal architecture, where you see at the zonal architecture you have the gateway. For instance, you have 2 gateways at the front, 2 gateways at the back, and 2 gateways in the middle, and they all are connected via Ethernet. Having said this, I'd like to hand over to Jitu, who will go more into detail.
Perfect. Thanks, Ralph. So with this transition to the zonal architecture, what I'd like to cover before we go into detail on what automotive Ethernet is, I'd like to look back on how in-vehicle networks have evolved over a period of time. So if we go back, let's say 3 decades later, we had something like CAN, which was very popular in the 90s, and MOS coming out as well. And over the decade or so on, then we saw a lot more bus activity here pop up into a car. So things like FlexRay, a lot more P2P based buses like USB, HDMI, and so on, and some more exotic SerDes applications as well. We also saw the start of Ethernet being built around about 2004, 2005. And this really was the start of trying to make sure that we have a networking architecture within a car. And as we all know, this has evolved and increased to a lot more different standards and a lot more different speeds. We saw the first dedicated automotive Ethernet-based communication coming out in just before 2010, but we also saw the evolution from CAN to CAN-FD, and then even more, sort of like what we see today in cars like A to B buses and so on. And as you can see, also for dedicated sensors, there's also been an influx of other different technologies in this space. And as we look at it today, we see a wide variety of interfaces out there for a car. So the most prevalent one from a networking architecture point of view has been Ethernet. And we see that being developed in speeds as well. Now we're here at 2.5 and even up to 10 gigabits per second, and even more, so up to 25 gigabit per second as well is being discussed. We also see the reduction of the speed as well, going down to 10, and also now the new standards coming out in CAN-XL and so on. So as you see, there's been a big influx of different technologies for different applications going around in a car. But what does this look like from a zonal point of view? So as Ralph showed in the last example, I want to take that example that Marvell had, where you have dedicated ADAS domain services or devices, let's say, and you maybe have body domain devices as well here. This communication between these could be CAN, could be slower speed Ethernet, and so on. And then they go into a zonal gateway or a zonal switch. This switch and the backbone here is Ethernet, and this is largely multi-gigabit Ethernet. So to transfer all of that data from each of the different parts or zones in the car to a central processing unit and so on to make the big decisions, and which is the brain of the car, let's say. So this illustrates the need for having really a perfect or a more reliable networking solution within the car itself. Now, we've seen this from all the different speeds and architectures and so on. I want to take it from another point of view, again, through where Marvell shows this, where you have, each of the different speeds have different applications as we went along the years. So we had low-res cameras at one point in time, but this went into, TCUs, went into more of a connected car architecture. And today we're talking about level 4, level 5, where it's ADAS and autonomous driving, where we have the push for having more faster speeds within the car. But it's not just from a speed point of view, it's also from the number of ports that we start to find, the actual Ethernet ports on a car, where each of these technologies have to be tested and so forth. I'll give you an example for where we find these speeds becoming more prevalent. So if we think about in a TCU application where we have lots of different channels coming in from different, be it wireless communication, be it LTE, 5G, or even V2X, for example, particularly for LTE and 5G, where you want to grab a lot of data, a lot of communication between a base station and a car itself. Within the TCU itself, you have your microprocessor, but how do you take that data across into the central brain or into the car? Well, that is through an Ethernet pipe or an Ethernet channel, and large and so forth, it is to a 2.5 gigabit per second automotive Ethernet standard that's being used. Of course, there are other different communications, like for V2X and so on, you have the URLCC. This is normally handled by different buses and so forth. But for this webinar, we will mainly focus on automotive Ethernet. So as you can see, there's a real requirement for these faster speeds within the car. But from our perspective, it's more to understand how do we test for these new technologies, new standards that are coming out. I have an example of a signal that we capture with a standard Ethernet. So this is a 100 base TX. readily available on most people's laptops or in any office environments and so on. I plug this into a scope to actually look at the time domain trace, and we can actually see 100 base TX is a PAM level 3 coded signal. So we have 3 different levels for all the bits, and we can see perfectly, laid out 3 clear levels for our signal. How does this look like for an automotive Ethernet signal? So this is the equivalent for a 100 base T1. So same speed, but in an automotive Ethernet scenario, we see it's way more slower rise times. The levels are not so well defined and so clear. And this is really to minimize any amount of EMI emissions or anything like this and so on, and still being able to communicate all the bits and so forth that the car needs. So as you can see, the needs for testing this becomes more prevalent and more important. Now, what does it come up to be when it comes to actual testing? So we have, as you see, the OSI layer, so from the physical all the way up to the application. And for today's webinar, we mainly will be focusing on the physical layer side. So as I mentioned, Ethernet has grown from 10 megabits all the way up to 10 gigabits in different standardizations. And this is really the requirement that most people have to make sure that their designs and so on are both compliant and able to send the data reliably. Of course, there's a lot more different tests and so on that we can do in all these different OSI layers. This could be down to, the correct latency or any kind of protocol transmission that you're doing. Are they accurate or not? Or if you wanted to validate any sleep or wake up cycles and so forth. So there's a lot of different tests, but again, for today's webinar, we'll be focusing mainly on the physical layer side. Now, for automotive Ethernet, there are different standard bodies that govern the automotive Ethernet side. So we have the IEEE 802.3, and as you can see in this slide, we have different working groups. So the CG, the BW, and the CH, for example, and they all have a specific task force, if you like, that are dedicated to different speeds and so on. And in here, as you can see, most of the speeds that we're talking about today, from 10 megabits to 10 gigabit, are all approved. They went through a range of different timescales, if you may, to get them approved and so on for various different reasons. But yeah, this is how the picture stays for today. Now, this is from an IEEE point of view. There is also another group called Open Alliance. Now, this is the group that actually is everything that relates to automotive is important to this group. So things like how we take the IEEE standards and how does that relate to how does the environment within a car itself look and so on. So it's made up of about 12 different promoters and largely more than 125 adopters and so on, and also mainly driven by a few of the key OEMs as well. And this alliance group also has different task forces as well. And for mainly the physical layer side, it's mainly TC8. For those who don't know, is for 100 and 1000 base T1. And this is an ECU test specification, let's say. And then the TC9, which is more about the channel itself. So the connectors, the channels, how do we take that data across into the other side? So they take care of not just on 100 or 1000, but they also take care of the faster speeds as well. TC15 is also the main working group for multi-gig Ethernet. So what do I mean by multi-gig? It's 2.5, 5 gig, and 10 gig Ethernet. And all these are a standardized working group, if you may, to get limits and all the compliance tests done so that you can be sure that whatever you're testing is adhering to those standards. To give you an idea how these different speeds look and differ, I have this slide here which shows all the different speeds, their relevant IEEE specifications, the Open Alliance groups, but also the bit rates and the baud rates. So each of the different speeds have different modulation schemes and thereby giving more amounts of bit rate. So for example, the 10 megabits has a baud rate of 12.5 megabaud, and this is realized by a differential Manchester encoding. So it's only a 2-level encoding scheme. However, for multi-gig, we go into PAM4, and this really goes into higher levels and so on so that we can actually get more of our data within a smaller space of time. Cabling has also changed. So we largely depend on unshielded twistor pair cables in the lower speed side because it's not so bad when it comes to getting that data across and so on, not so much susceptible to EMI. But when we go in higher speeds, shielded twisted pair cables become more and more important and prevalent. Now, from a testing point of view, what does that look like for Rohde & Schwarz? So we have a range of different test solutions, all adhering to the Open Alliance test specifications, as you can see in here. We cover from the 10 megabit all the way up to 10 gigabit speeds. From a compliance, PMA compliance point of view, but also for trigger and decode to actually find out if there are broken messages or error messages or so on. We have our VNA solutions that look at characterizing cables and connectors and so forth. And we have software as well that allows for automated testing to make this all possible. As an example, I have our solution for our multi-gig base T1. So this is our fairly newest solution for multi-gig base T1 PMA compliance test. So this covers 2.5, 5, and 10 gig. And largely, as you can see, we have a lot of different test cases that we have to test for. This could be things like, how much jitter there is coming from the signals that you're looking at, or how much of power spectral density does the board have and the designs have. The software itself works on the scope or on a laptop, and it allows you to actually guide through, select the measurements that you need, and do all the automated testing on the scope or the VNA. Now, all of this can be done through a reporting tool as well. So you get a report functionality at the end of it to show you where you passed, where you failed. So for multi-gig, there's a variety of different tests that some person who would have to adhere to this Open Alliance standards, or even for that IEEE standards, would have to adhere to. And this is the list of PMA tests we have, the receiver tests, and also the impedance requirements that the MTI needs to go through. So all of this is covered by our solutions. I want to stress the point that, especially for multi-gig, it's still going through the Open Alliance test specifications and so on. So the group is very active in trying to define and make a final draft or the specifications available. So this is going on at the moment right now, and this will be heavily debated and so on to exactly what those test conditions should be and what they should entail. Now, to give you an idea of what this looks like on our solution, I'd like to give you a quick demo of what this looks like on RTP oscilloscope. For today's demo, I have with me a multi-gig Ethernet evaluation board. This is from Marvell as an example. And we've connected this to the automotive Ethernet plug wire. These are the Rosenberger plugs, which gives us access to the actual electrical signals via SMA adapters. And from here, we can then connect these two SMA cables directly onto our oscilloscope on channel 1 and channel 3. And as you can see on the screen, we now have our multi-gig. At this point in time, we've configured the board to be 10 gigabit, and we can see our PAM4 signaling there as well. So all the 4 different PAM levels for this signal. Now, once we have the signal, I want to make sure that is this compliant to all the different Open Alliance or IEEE standards. And for this, within the scope itself, I have, if I go into the menu and into the apps selection, I can have a selection for all the compliance technologies that I can test for within this scope. So let's go ahead and select multi-gig. And then this brings up our software here, which is again installed on the scope to actually tell us which of these different standards we have and so on. And I'm going to select multi-gig here. And as you can see, I have my different speeds, 2.5, 5, and 10 gig for multi-gig. And the software itself works in different sessions. So if you had a variety of different test boards or different sessions and so on, you can add a new session in here. And then once you open this session, as you can see in the background, it starts talking to the scope remotely and also then sets up the scope to all the parameters it needs to do. Now, on the left-hand side of the GUI, you can see that we have all of our test cases that adhere to 10 gigabit speeds, and we have all our properties. So to say things like where our data is connected, either channel 1, channel 3, for example, if we have any skew, and any of the test parameters that we perhaps want to change. It's important to note that for all of these test cases, there are also different test modes that the PHY has to support. So if you aren't aware of this, please reach out to your PHY vendors and they'll be able to help you understand how to put these your different PHYs into these different test modes. So for today's example, I've taken a test mode 5, and within here, we're actually testing for the power spectral density and also for any differential peak outputs that we're seeing. So actually measuring those values. So this is just one example that I wanted to show you. Of course, we can go through all of these, but for today's webinar, we'll just take this one as an example. So in here, I can select all of them or a particular test case I want to check for. And as you can see on the right-hand side, it gives me just the properties I need for this particular test case. Now, let's go ahead and run this test. And what happens in the background now you see on the scope is that it sets up the scope to actually start capturing. So here where it's asking us to connect to channel 1 and channel 3, and then just as a sanity check telling us that, okay, this is the expected waveform, and then you can cross-check that to see, yes, that's the right waveform that I expect to see, all my 4 PAM levels. It then goes away, and now because we have a single-ended connection on the scope, it then sets up a differential math signal and then performs various scaling and various measurements, if you like, on this particular signal. Now we selected for this test case was the power spectral density, and in the background you can see the FFT comes up, the math function, all the different mask values and so on are put up. And we also see a progress bar on how this is being pulled through, how the data is coming through and so on. Again, minimal use from the user itself to know what settings to do, what parameters to change and so on. The software itself takes care of all the settings, all the measurements and so forth. And once it analyzes that waveform and performs all the tests, makes sure that there are no violations to this mask. And also, we're also doing our peak differential output, don't forget. This also is being measured on the scope, if you like. And then once that is done, it'll then give us the results. So have to wait for a few more seconds. And then once that's done, as you can see, we get a nice green tick to say, yes, this is passed this test. Now, at this point, we can run through all the different ones. But for today, I'm just going to go ahead directly into the show reports section, where it now will generate a PDF report for me on all these different test cases that we have. So let's go ahead and minimize this. And you can see this is the only test case that we had in this test session was test mode 5. Of course, we could have put a DUT naming, a device naming to this, but we're maybe more interested in the measurements itself. So you can see here what measurements were being done, a quick snippet of what the measurements is actually being done, what the pass is, what the failure is, and so on, how that adheres to the limits, but also screenshots as well to show you, okay, how these measurements were performed. We also see for what the maximum and the minimum values were in our peak differential voltage test as well. Now that we've seen the demo, I'd like to go through very quickly as well what we have in terms of cable and channel testing. So for the TC9 part, where you have the twisted pair or the shielded twisted pair cables, this also becomes a big topic to actually look at the whole chain. So where we have a connector maybe in line, or the cable itself, and how does that perform in terms of getting the data across to our receiver side. So we're looking at things like, how much loss there is, how much return loss, maybe insertion loss as well, and also how much impedance to actually look at from a TDR point of view, where exactly we might have reflections and so on. For more details on this as well, please look at our website. So we have lots of content there to actually look through and see how to perform some of these tests and make sure that cables and connectors and so on are also verified to the Open Alliance standards. So as a quick summary from a test solution point of view, as you see, testing becomes more and more important as we go into these higher speeds. The topic about signal integrity and making sure that we have defined 4 PAM levels and so on, and no artifacts or any errors and so on, becomes even more important. So we have a full range of different testing capabilities, as you can see there, supporting different speeds, be it from the VNA point of view or from the oscilloscope point of view, to look at an overall range for any physical layer tests that you would need to do. And with that, I'd like to hand back over to Ralph to give us a quick summary.
Thank you very much, Jitu. Very interesting and impressive. So let's summarize today's webinar. What did we see? What did we hear? We're already in the future. We all experienced most of the parts that we spoke about this. So the car of the future is apparently autonomous, connected, electrified, and shared. So with the domain centralized architecture, we can already experience driving up to level 3. And in the near future, with the zonal architecture, we can even drive above level 3. So level 4 and maybe even level 5 quite soon. Fast and flexible in-vehicle networks support this high computing power and the high data throughput, which is necessary for that. And a multi-gig Ethernet backbone enables fast and flexible data transmission within a vehicle, as shown by Jitu. Also, shorter vehicle wiring harnesses reduces cost and weight, as we could experience with the zonal architecture. The compatibility and performance of different vendors' equipment can be ensured via Open Alliance compliance testing, thanks to Rode and Schwarz. With that, I would like to thank you. I hope you enjoyed our webinar today. Should you have further questions, please feel free to visit our website or contact your local sales manager. Thank you very much.